We're going to talk a little bit about energy. We're going to talk a little bit about metabolism. We're going to define energy as the ability to do work. We're going to talk about it in the context of the first and second laws of thermodynamics. And we're going to talk about energy in the form of kinetic energy and potential energy, and what that means in biological systems and how we harness the energy of both of those kinds. Okay. And we need that to harness that energy so that we can perform metabolism. We can talk about, and we've already introduced these terms of anabolic and catabolic. And we're going to talk, again, like I mentioned previously, we're going to introduce enzymes and talk about their function and how they work and why they're so important for living systems. Okay, so section 1, where you need to figure out the difference between kinetic and potential energy. We need to identify what the source is for energy for living systems. And then we're going to talk about these redox reactions. And this is the concept that we're going to come back again. So when we get to chapter 7 and we start talking about cellular respiration, and again when we talk about photosynthesis, we're going to want to remember what we learned today about these redox reactions. All right, so the word thermodynamics literally means heat changes. Okay, so this is how we are going to transform energy. We talk about energy in the form of heat because it's the easiest way to measure energy. And we, as biologists, we need to understand the laws of thermodynamics because, as we already know, we already talked about in chapter 1, that biological systems are also subject to the laws of physics and chemistry, and therefore must follow the laws of thermodynamics. And we'll talk about what this means for how cells use energy. All right, so energy, we're going to define this broadly as the capacity to do work. Kinetic energy, right? This is our energy of motion, and potential energy, this is stored energy. So here I have a picture of Glen Canyon Dam. This must have been in the 80s when this photo was taken because there's water in Lake Powell. We've had some scary times in recent years of like, are we still going to be able to produce energy from that dam? But right, so if we broke that dam down, all of that water that's being stored and behind the dam, we pull that down, all of that energy is going to change from potential energy into kinetic energy as the water rushes down. Okay, and so we can see that here in this stream. So, oh, I didn't prepare well enough. I have a dog toy. Okay, so if I raise this little squishy ball, the higher that I raise it, the more potential energy that it has. And as soon as I drop it, right, that potential energy is going to turn into kinetic energy as the ball starts to fall. Okay. So any of that stored energy, that potential energy can turn into kinetic energy. Right. Potential energy is also can be our chemical energy, right, that we see in our chemical compounds, right? So we talked about carbohydrates earlier in the semester, and how we're going to, and then later in the semester, we're going to talk about how we take that stored energy in those glucose molecules and break it down to release that potential energy so that we can use it to create ATP. Okay, so the first law of thermodynamics states that energy cannot be created or destroyed. It's only going to change forms. And there's lots of forms of energy: mechanical, heat, sound, electrical current, light, radioactivity, right? All of these things are ways that we can have energy. In biological systems, we're going to talk a lot about heat. We're going to talk a lot about light. We're going to talk a lot about chemical energy. We talk a little bit about kinetic energy. Okay. And what's interesting is that every time we change forms, some of that energy is also transformed to heat. And because we're talking in the biological context, that heat is lost to biological systems because cells are not good at using heat as a energy source. So when we talk about some of that energy being lost as heat, It's not being lost to the universe, right? It's just changing into a form that living systems can't really utilize very efficiently. All right. So ultimately, the energy that we have available for living systems comes from the sun. So without the sun, biological systems are kind of screwed. If our sun suddenly shuts off, we have 8 minutes before all of our systems start to die out, right? So right, we of course we know already from like our previous knowledge that the sun is going to power photosynthesis, which is going to provide food for the whole rest of the ecosystem, okay, including humans. Okay, again, loads more details on photosynthesis coming up later in the semester, okay? But what these photosynthetic organisms are going to do is be able to capture that light energy and turn it into potential energy in the form of those chemical bonds that we have in glucose that we can then, us heterotrophic organisms, can use to power our mitochondria to make ATP. All right, so here's our redox reactions. Again, this is a concept that we're going to come back to multiple times over the semester. So like it's worth understanding now. It's worth trying to put some effort into so that we can really make sure that we know what's going on when we get into those more complicated chapters, chapter 7 and 8 specifically. All right. So a redox reaction, these are actually two reactions that are always paired, and we'll see why here in a second. So here's my, so in a redox reaction, what we're going to do is we're going to transfer an electron. So here I'm going to use my dog toy again as representing an electron. So if my left hand has the electron and it's going to give it up, it wants to donate this electron, there has to be something else that can receive that electron. So when the particle, whether this is an atom or a molecule or whatever, donates the electron, we say that it is oxidized. And then the particle that receives the electron, we say is reduced. Okay, so like, all right, hold on, Julia, just a second. I'm really confused now because you just said the thing that gains an electron is reduced. Well, remember what the charge is for electrons, right? Electrons have a negative charge. So if you're gaining electrons, you're actually becoming more negative, and so you're becoming, your value, if you will, is becoming reduced because we're gaining those electrons. We're becoming more negative, okay? And what we see is the particles that are reduced that have that extra electron, those are going to be in a higher energy state. Okay, and again, we're going to want to remember that later in the semester. So I will remind you, but it's worth keeping in your brain for now. Okay, and again, these redox reactions, the reduction and oxidation reactions are always paired because that electron, if it's going to get donated by something, something else has to receive it. So they are two reactions, but we smush them together. We portmanteau those words into redox.